Hey there, and welcome back to another tutorial. It's been some times, and I saw a lot of talented people that already did impressive stuff with PCG, which is super cool to see. Also, a lot of people added video and tutorials on PCG. I can only encourage you to go see the latest presentation from Chris Murphy at Unreal Fest Prague 2024, even if it's throw me under the bus saying that YouTube tutorials are all doing the same thing. Thanks, Chris. All the links will be in the description. 5.5 is around the corner, and it's packed with new features that were in the making for a long time. I have a few videos planned to present these new features, but for now I want to come back to something that was requested a lot and not always well understood: generation modes. I'll build up on the already available documentation, trying to provide some hints on how to optimize the flow for performance. The link to the doc is in the description, and it's a good page to bookmark for a refresher. Shout out to my colleague Hugh, that was the original author of the video internally, and asked me to revisit it for the public. We'll see how we can try to scale our generation to bigger maps, what is partitioning, hierarchical generation, etc. If you wondered what was the PCG World actor or the PCG Partition Actors, I'll cover it there. It won't be an impressive demonstration. I'll stick to very simple graphs to highlight exactly what are the bottlenecks when generating and how we can achieve good results and packed meshes without tanking the frame rate. As always, the material will be available on the GitHub, and you can join the community on Unreal Source channel PCG Framework. There are a lot of people there that starts to know what they are talking about, so that's a great place to ask for help. Alright, let's dive right into it. For this tutorial, I'll work on a bigger map since we tried to generate at scale. I'll start by creating an open world map with the default 2x2 km landscape and save it. I'll create a simple graph and drag it into the scene to create a PCG volume, and I'll center it into my world. Opening the graph, I will go with 4 nodes: get landscape data node to query the landscape, a surface sampler to sample the landscape, a transform point to add more variety, and a static mesh spawner with the 3 tree meshes that come with the PCG plugin. To see them, make sure that you have show plugin content enabled. Classic, simple, and already a good use case to see how it scales on this big map. I'll enable the FPS counter and the unit graph to track performance. Little disclaimer, I have a high-end PC, a Ryzen 9 7950X with RTX 3090 and 64 GB of RAM, so it's possible that the generation will be long for less powerful PCs. So when you scale the volume to extend the generation, don't go ham too quickly. If I inspect the result of the generation with the A key and clicking on the component in the bottom left, with a volume of scale 25, I get 156 points. And to see the exact cost of the generation, since some of the nodes were cached, I forced the regeneration with a Ctrl plus click on force regen, and it gives me a generation time of 2 milliseconds. Quick explanation on the total time versus the wall time. The wall time is the real time between the start and the end of the execution, while the total time is the time actually doing stuff in PCG. Since PCG has a time budget that you can set with pcg.editorFrameTime or pcg.frametime for runtime generation, when the budget is totally consumed and the current task is done, PCG will give back the control to the engine and will be ticked again at the next frame. In my case, you can see that the total wall time is 14 milliseconds, while the total time is 2 milliseconds. Since my refresh rate is 100 Hz, so 10 milliseconds per frame, it means that PCG executed over 2 frames. So let's increase the size of the volume to see exactly how it scales. With a scale of 100, it took 15 milliseconds to generate, and we have 2500 points. Of course, most of the time is spent in the static mesh spawner, pushing a lot of instances into an instant static mesh component, especially with collision enabled, is expensive. I'll scale it even more to 250. We have more than 15k points, and it took more than 100 milliseconds. And covering the world with 1000, It freezes the engine and took more than 2 seconds. So yeah, you can't really expect to have a big PCG volume that will hold the full generation. Even worse, since the volume is enormous, it will always be loaded in-game and won't benefit from streaming. If I move my player start high in the sky and start pi, it takes some time to start the level, and you can see that the whole forest is loaded. To illustrate the streaming problem, I will add a big cube at the extremity of the map. It won't be loaded because it is outside of our loading ring, but the whole forest is loaded because all the instances are part of the same actor under the same component. It's clear we can't use a single volume to populate a big map with PCG. Fortunately, there is an integrated solution to dispatch the generation to smaller actors. It's the isPartition option on the PCG component. But first, I'll scale the volume down. If I toggle it on, it automatically regenerates with this new mode. And you can see that the PCG volume doesn't hold the meshes anymore. That's because the generation was dispatched to the local actors called PCG Partition Actors. Those actors are automatically created by the PCG subsystem and are under the PCG World actor. If I click on some trees, you can see that the part of the generation is under the PCG Partition actor. PCG Partition Actors are set on a grid, and you can set the grid size on the PCG World actor. By default, the grid size is 256 meters, but we can make it smaller if we want, like 128. It will spawn new actors at this size. If I make the volume bigger, we can clearly see the grid limits. Partition actors that are not used anymore should be automatically cleaned. But if you ever get in a situation where you have zombies partition actors, you can nuke them within Tools, PCG Framework, delete all unused PCG partition actors. Now, if I scale the volume to cover the full map again, you can clearly see the grid pattern generation. It generated a lot of actors, so be careful to not set the grid size too small, as it is heavy on the number of files, and usually source control like Perforce doesn't like that. If you need more flexibility with the grid sizes, we'll see later how we can have multiple grid sizes with Hierarchical Generation. In the meantime, in Pi, with this new generation, you can clearly see now that far away actors are not loaded, which is a good thing if your scene is way more loaded than simple geometry meshes. You probably want to combine partition actors with HLODs generation for a performant open world presentation. If I build the HLODs for this map, and be careful doing it like this, it's very heavy on the RAM. And relaunch Pi, you can see that the whole forest is there, with the PCG partition actors loaded close to the player, and the HLOD for the farthest actors. Alright, we saw how we can scale to bigger maps with partition. That's nice, but can you just toggle isPartition and get a 3 ticket to better performances? Actually no. While some graphs can just toggle that on and give the same results, there are some pitfalls I want to mention before going to Hierarchical Generation. So I will start again from a clean state, so we'll clean up my generation, and I will also delete the HLODs for the forest and then rebuild them for the landscape. I'll craft a simple example to illustrate what could go wrong. I create a new graph that I'll name simply grid, drag it into the world, and set the scale to 100. I open the graph and add a node create points grid. I'll set the grid extent to a big number like 10,000, 10,000, and 50. And for the cell size, I will go with 500, 500, and 100. I'll inspect the node and it gives me 1600 points. By default, this node generates points at the origin. You can change that directly in the node, but for the sake of an example, I'll do it myself in the graph. To bring back the points on the actor, we have multiple ways of doing it. The easiest way is copy points from the actor point. For that, we'll use the getActorData on self as a single point. And because the point we have a volume scale, I will use the node's apply scale to bounds to reset the scale to 1. It's important for copy points, otherwise the scale will mess with the copy. What this node is doing is very simple, it'll just multiply the bounds min and max by the scale and reset the scale to 1. And I'll add the copy points node, where my source points are my grid points, and my target is my actor. And I will debug the result. To see the grid better, I'll add an extend modifier node after the createPoints grid node to slightly reduce the bounds of the points so we clearly see the grid. Alright, now if I enable each partition, what is happening? The grid seems to be copied to all intersecting partition actors. It's even clearer if I move my volume so it intersects with more partition actors. So why is that? It's actually coming from the getActorData. Since self is now the partition actor, we are copying the results of our grid to self. So each partition actor will execute and copy the grid to itself. That's not what we want. We want the position of the original component. Fortunately, you have the option original instead of self on getActorData that does just that. And you also have the option directly on the createPoints grid node. So now it seems to work, but is it really? If I click on the cubes, you can see that the same cubes appear on multiple partition actors. If I inspect the copy points, I have the same number of points for each partition actors. We are clearly duplicating some work there. When working with partition components, it is important to restrain the work to within the partition actor. Otherwise, we can do the same work multiple times. To do this, we can use the intersection node. With getActorData self, and this time self is what we want. And with that, we can see that each partition actor is responsible to debug only the cubes that are within its bounds. Alright, so we saw how we can partition our component to dispatch the generation to smaller actors, and a few pitfalls to avoid when going from non-partition to partition, namely making sure that the data we get is coming from the right source, and that we don't do the same work multiple times by constraining the generation to the partition actor. Now, let's dive into the wonderful world of hierarchical generation, HyGen for short. I'll go quickly on HyGen without runtime generation, because HyGen is an extension of the normal partition system. With HyGen, we can have multiple grids of generation and assign part of the graph to execute at a given level and use data from upper levels. We saw earlier how many actors we can create with a 128 grid. If we start going with even smaller grid sizes, it can make the number of actors explode. So we'll see a simple example with a small volume, then we'll move to runtime gen. So we'll start from scratch again. I will delete my previous volume and create another graph, PCG HyGen. I'll drag it into the map and place it at a very precise position for this example, which will be 15,000, 15,000. To enable HyGen, we need to mark the component is partition, and also enable HyGen in the graph under graph settings, use hierarchical generation. HyGen works with grids of size of power of 2. There is a default grid size that will define the biggest grid for this graph. By default, it's 256 meters, which means that the graph will generate inside partition actors of size 256. Let's try it out quickly with a landscape, surface sampler, and debug to see the partition actors. You can see that it generates inside one partition actor of size 256. You can also inspect a given partition actor, and you'll see on each node at which grid size it was generated. I can change the default size to something smaller, like 32 meters, and you can see that I have now more partition actors with their own cubes, because the surface sampler is taking the actor bounds by default to constrain the generation. And if I inspect one component, you can see that nodes are generated at grid size 32. There is also an option unbounded, which means that the generation will be run on the original volume directly, as if it was not partitioned. You can see that the cubes are attached to the volume and not the partition actors. And if I inspect again, it is marked UB for unbounded. For the rest of this example, I will switch back to 256. That's not very different from the previous way of partitioning PCG. So now let's introduce grid size nodes. Those nodes act like gates you can place in your graph to force everything downstream to be executed at a given grid size. The idea with that is that you can compute data at a higher grid and use it at a lower grid size. We'll set this grid size to 32 meters and place it between our surface sampler and our debug node. We have the same result as before, the cubes are on the 32 partition. But we are encountering the same issue than before, is that the cubes are duplicated on all partition actors. To fix that, it's pretty simple actually, and clearer when we inspect the graph. Let's select a 256 partition actor. You see that the sampling is done at the 256 level. It is executed first, and then the grid size of 32 stops the execution at 236. Then the 32 partition actors generate the same graph, starting from those gates and inheriting the result. Of course, in that case, we have the result on the 256 partition actor, so just one actor. So we get this data directly on each 32 partition actor, and we feed it directly on the debug. That's duplicated work. All 32 partition actors are spawning the same set of points. That's where the other pin of the grid size is useful. We can use it to filter the data that is inside our cell. So let's add an intersection node, and now each 32 partition actors is spawning cubes within its bounds. Because of the number of actors it generates, especially at lower grid sizes, it can be limiting pretty quickly. But there are still a lot you can do with just that. But where HiGen really shines is when it's combined with Runtime Generation. With Runtime Generation, we can skip the actor creation on the whole volume, but only generate the actors that will be inside our Runtime Generation ring. Let's start fresh again, deleting my volume. I'll create a new PCG graph, PCG Runtime HiGen, drag it into my world, set it bigger, make it partition, and enable HiGen in the graph settings. I'll also set the default grid size to 128. I will redo the same simple graph to spawn some trees. To turn on Runtime Gen, we need to change the generation trigger from generate on load to generate at runtime. But when we do so, everything disappears. But that's normal. Generation is only done at runtime, so we just have to start pi. And indeed, the trees generate at runtime. They are floating, that's because I made an error on the transform point, I will just fix it. It's a bit tedious to have to start the game to see the results. To mitigate this, you can enable the editor viewport camera as a generation source on the PCG World actor. Enabling that, and you have Runtime Generation actors that are spawned. But what is a generation source, you might ask? That's a great question. To know which partition needs to generate, we have a concept of generation source, similarly to streaming sources. By default, the generation source is the player's camera, and its policy to generate is to generate everything within a given radius for each grid size, and prioritizing generation for all partition actors, that are in the first room of the camera. Basically what it means is that it will prioritize what the player sees first, what's in front of them, and what's behind will be generated afterwards. This whole generation source concept and its policy are fully customizable. It's all under Runtime Generation in the PCG component. To change the radius of generation for each grid size level, you can enable override generation radii. If I make the volume bigger, you can see that the generation is only done around the viewport camera. If I move, the generation will be triggered for new cells. I can also change the generation radius. Since I'm at size 128, I'll reduce this number a bit. And it reduces the radius of the generation. If I make it bigger, it will increase the radius. Let's combine this with Hygen. I'll reduce the density of the trees, and I will try to spawn some rocks on a smaller grid size. I add a grid size node of 64, and I will gate the landscape data. Everything downstream of this node will be generated at grid size 64. Then I will do exactly the same thing as the trees for my rocks. And now you can see that the rocks are on partition actors of size 64. Of course, we can have trees that overlaps with the rocks. So we'll use the difference node as always. I want to remove from my rocks the point of the trees, set it to binary, and now my rocks are not intersecting with the trees anymore. If I inspect the 128 partition actor, you can see that the top of the graph is generated at this size, the rock branch is not executed at that level. And if I select the 64 partition actor, the bottom of the graph is generated at this level. It also uses data coming from the 128 partition actor. Only smaller grid size can use data from higher levels, not the other way around. To tidy my graph, I'll create name reroutes for my trees and rocks. I'll redo the same for grass at an even smaller grid size. I'll make the surface sampler denser. And then we do the same with transform points. Difference. And spawning, and making sure that the spawning is done with no collision to speed up the spawning since we don't need collision on grass. And then I have my denser grass, and if I move around, it generates automatically. The exclusion is not very good, so I will change the bounds of my rocks. And also change the difference on the grass for binary. And the grass is a bit too big, so I will reduce it. And that's how we can build a hierarchy of generation at runtime. As a little bonus, let's go even further, with some seedling also spawn on rocks, using the mesh sampler. As a reminder, the mesh sampler is using geometry script underneath, so we need to enable an extra plugin, PCG geometry script interrupt. We're going to sample the border mesh, and we don't need it to be done every time on all partition actors. We can do it only once, and that's where unbounded is becoming very handy. I'll change the graph so my trees will stay at 128, but we'll change the default to unbounded. I'll add a mesh sampler node, make it a Poisson sampling, and select my border mesh. If you remember episode 3, the mesh sampler is creating the points at the origin, so we need to copy the points on each rocks. So I will add a copy points node, with the source being the mesh sampler and the target will be my rocks. And if I add a debug node, you can see that I have points on all my rocks. If I inspect a partition actor where my rocks are, you can see that the mesh sampler is only done once at the top level, but the copy points will be done only at the 64 level. To increase the number of points on my rocks, I can go into the Poisson sampling and just reduce the sampling radius to 5 so I have more points. Now I only want to keep the points that are on the top of my rocks, meaning a normal that is pointing up. To filter that, I can use normal to density. You can see that the points that are facing up are wider and the others are darker. I can keep only the white ones with an attribute filter. I want to target the density and only keep the points that have a density higher of 0.7. And so you can see that I have my points there. Since we'll spawn seedlings on the rocks, it makes sense to put it on the same size as the grass. So we will gate the points coming from the rocks with a grid size node of 8. And also we don't forget to use the intersection node to make sure that we are not duplicating the work and only get the points that are within our partition active bounds. Now you can see that the points that are on the rocks are on the same partition actors than the grass. Finally, I can add a transform point and play with the scale and the random rotation. And since I want to spawn exactly the same mesh, I can just plug it directly into the static mesh spawner of the grass. Nice. And of course, it continues to generate at runtime within our generation radius. For even more randomness, I can select a certain ratio of points from my sampler. Now each rock has a different pattern. Quick review of the final graph. We have Hygiene enabled in the graph settings with our default grid size at unbounded. The get landscape data node is executed only at the unbounded level. Then we have a sampling branch on the 128 level because of the grid size node of 128. Then at the 64 level, we have our rocks, and at the 8 level, the grass. For the seedlings on rocks, the mesh sampler is only executed once at the unbounded level, and we do the spawning on the 8 level. This concludes this presentation of the different geometric modes. I hope it was useful, and I see you in the next one. In the meantime, have fun with the plugin. Take care.